Imagine a black hole so massive that our entire solar system, every planet from Mercury's scorched surface to Neptune's frozen orbit, could vanish inside its point of no return. Now imagine that boundary stretching 14 times farther than Neptune's path around our Sun. This is TON 618, a gravitational abyss weighing as much as 66 billion suns, blazing with more light than 400 trillion stars, and existing at a time when it shouldn't. You're about to discover how astronomers found this cosmic leviathan, why its existence breaks our models of the universe, and what happens to space, time, and matter in its vicinity. If you're ready to explore the most extreme object ever detected, smash that like button and hit subscribe. Let's dive into the abyss. The accidental discovery of a monster. The year was 1957. French astronomer Marie-Hélène Ulrich aimed her telescope at a faint smudge of light nestled in the constellation Canes Venatici. She logged it as entry number 618 in the Tonnant-Zintler Observatory catalogue. The notation was routine, clinical, another dim point among billions scattered across the cosmic canvas. Nothing suggested she was cataloguing the most massive single object humanity would ever discover. For decades, TON 618 gathered dust in astronomical records. Researchers assumed they were looking at a distant star, perhaps a small galaxy. The instruments of the 1950s and 60s couldn't penetrate its secrets. Spectrographs produced blurry data. Distance calculations remained educated guesses at best. That pale glow was concealing something monstrous, but technology hadn't caught up to revelation. The 1970s brought better tools. Astronomers began dissecting the light signature emanating from TON 618 with improved spectroscopy. What they discovered sent shockwaves through the community. The spectrum showed extreme redshift. This object wasn't moving away from us slowly. It was hurtling through the expanding universe at tremendous velocity. More, crucially, this redshift meant TON 618 wasn't nearby. It wasn't even in our cosmic neighbourhood. The light reaching Earth today departed TON 618 when the universe was a mere 3 billion years old, less than a quarter of its current age of 13.8 billion years. We're witnessing a snapshot from the cosmic dawn, looking backward across 10 billion light years of space and time. Then came the truly unsettling revelation. When scientists measured the energy output from this tiny dot in the sky, the numbers seemed impossible. This object, barely visible to our instruments, was pumping out more radiation than entire galaxy clusters. Something 10 billion light-years distant should register as virtually nothing, a whisper against the cosmic background. Instead, TON 618 roared with the fury of 400 trillion suns compressed into a region smaller than our solar system. Only one explanation fit: a supermassive black hole in full feeding frenzy, surrounded by a superheated disk of doomed matter, spiralling toward oblivion. But when researchers calculated the mass needed to generate such overwhelming luminosity, their models broke. The mathematics insisted TON 618 weighed 66 billion solar masses, a figure that shattered every record and violated everything cosmologists thought they understood about black hole formation timelines. Most galactic black holes measure millions of solar masses, perhaps a few billion in the largest galaxies. TON 618 crushed those records. It weighed more than some entire galaxies. It exceeded the mass of smaller galactic collections, and it achieved this impossible size when the universe was young, before sufficient time existed for it to grow through conventional feeding. The discovery ignited fierce debates across astronomy departments worldwide. Some scientists dismissed the measurements as instrumental errors or calibration problems. They argued that no object could be this massive this early in cosmic history. It violated fundamental principles of black hole growth. Others proposed wild theories involving direct collapse from primordial gas clouds, or massive mergers of smaller black holes in the dense, chaotic early universe. Every explanation required bending or breaking the established rules of physics. Confirmation came from multiple observatories using entirely different methodologies. Radio telescopes detected intense emissions characteristic of active galactic nuclei. The radio signature showed the telltale patterns of matter being accelerated to near-light speeds in powerful jets. X-ray satellites picked up the unmistakable signature of matter being torn apart and superheated to billions of degrees. Optical telescopes measured the Doppler shift of gas clouds whipping around an invisible gravitational anchor at thousands of kilometers per second. Infrared observations revealed the structure of the surrounding dust and gas being heated by the central engine. Every instrument, every wavelength, every measurement technique agreed. TON 618 was real, and it was enormous. Today we understand TON 618 anchors a distant galaxy we can barely resolve against the glare of the quasar itself. The black hole remains invisible. All black holes are invisible by nature, but we detect it through its violence. Matter accelerates to nearly light speed, heats to incomprehensible temperatures, and screams electromagnetic radiation across every wavelength before crossing the event horizon and vanishing forever into the void. Understanding TON 618 fundamentally changed how we think about black hole formation and cosmic evolution. It revealed that the early universe was far more violent, chaotic, and rapidly structured than our comfortable models had predicted. Massive structures formed faster than they should have. The rules we thought governed cosmic architecture needed complete rewriting. The discovery forced cosmologists to reconsider everything they thought they knew about the first 3 billion years of universal history. But discovery was merely the beginning. Measuring its mass presented one challenge: comprehending its actual scale. The physical enormity of 66 billion solar masses concentrated in a single gravitational well would prove far more disturbing. Because when you calculate the size of TON 618's event horizon, you realize we're dealing with something that challenges not just our instruments, but human imagination itself. The impossible mathematics of mass. Calculating the mass of an object 10 billion light-years away sounds impossible. You cannot place it on a scale. You cannot send probes to orbit it. You cannot even see the object directly. Yet astronomers determined TON 618 weighs 66 billion times more than our Sun. And when the first results emerged, research teams threw them out and started over. The numbers were too extreme. Something had to be wrong with the calculations, the instruments, or the fundamental assumptions. The technique relies on luminosity, how brightly a quasar shines. The physics is elegant and well-tested. When matter falls toward a black hole, it doesn't plummet straight down. Angular momentum and gravity force it into a rotating disk structure called an accretion disk. Friction between particles in this disk generates tremendous heat. The inner regions, orbiting fastest and experiencing maximum friction, reach temperatures of millions or even billions of degrees. That heat produces light across the electromagnetic spectrum. The brighter the quasar, the more matter is falling in. The more matter falling in, the stronger gravity must be to capture and accelerate it. The stronger the gravity, the more massive the black hole at the center. Scientists can work backward from brightness to mass using well-established physics. The relationship has been tested across thousands of quasars and active galactic nuclei. The mathematics is sound, proven, reliable. The problem was that the math kept insisting TON 618 weighed 66 billion solar masses. Early research teams assumed equipment malfunction. Perhaps the detectors were miscalibrated. Maybe atmospheric distortion was amplifying the signal. They recalibrated every instrument and measured again. Identical results. They used completely different telescopes on different continents, eliminating systematic errors. Same answer. They employed multiple independent techniques, measuring brightness at different wavelengths, analyzing spectral line widths, studying variability timescales. Every method converged on the same impossible number. They checked for gravitational lensing. Perhaps another massive object between us and TON 618 was magnifying its light artificially, like a cosmic magnifying glass making the quasar appear brighter than it actually was. Extensive surveys found no lensing galaxy in the line of sight, no gravitational distortion patterns. The light was intrinsic, not amplified. They considered whether multiple black holes might cluster together, creating a combined signal that mimicked a single supermassive object. The spectral signature showed a single unified source with characteristic patterns of a single accretion disk. Multiple black holes would produce distinct spectral features, additional peaks, unusual line ratios, variability patterns. None of these signatures appeared. One researcher proposed TON 618 might be experiencing a temporary feeding surge, consuming an entire galaxy's worth of material all at once, and artificially boosting brightness beyond its normal state. but the quasar had maintained stable output across decades of observation. Archival data going back to the 1950s showed consistent brightness with only minor variations typical of all quasars. Whatever was happening wasn't a temporary flare or unusual event. This was normal operation for TON 618. The resistance to accepting the measurement stemmed from a fundamental problem in cosmology. Black holes grow by consuming matter. They eat gas, dust, stars, and anything else gravity delivers to their vicinity. Each meal adds mass incrementally. But physical limits govern how fast a black hole can feed, limits imposed by the laws of physics themselves. This constraint is called the Eddington limit, named after British astrophysicist Arthur Eddington, who first described it mathematically in the early 20th century. The physics is straightforward but profound. When matter falls toward a black hole and accelerates under intense gravity, it gets compressed and heated through friction and collisions. This heating produces intense radiation, light, X-rays, all forms of electromagnetic energy. That radiation exerts outward pressure on any additional matter trying to fall inward. Photons carry momentum, they push on things. Eventually, if enough matter is falling in and producing enough radiation, the outward radiation pressure precisely balances the inward gravitational pull. At this equilibrium point, called the Eddington limit, matter cannot physically fall in any faster. Additional material gets blown away by radiation pressure before it can cross the event horizon. The black hole has reached its maximum sustainable feeding rate for its current mass. This creates a fundamental speed limit on black hole growth, an absolute ceiling on how fast mass can be added. The Eddington limit isn't negotiable or avoidable, it's a direct consequence of radiation pressure opposing gravity. For a black hole feeding continuously at the Eddington limit without interruption, physicists can calculate precisely how quickly it can grow. The growth is exponential. The black hole doubles its mass every roughly 50 million years when feeding at maximum rate. Starting from a stellar mass black hole formed from a massive star's supernova, perhaps 10 to 100 times the Sun's mass, and feeding continuously at the Eddington limit for 3 billion years, you reach approximately 1 billion solar masses. Maybe you could stretch to 10 billion solar masses if you pushed every assumption to its absolute breaking point, assumed perfect conditions, perfect efficiency, perfect continuous feeding without any interruptions. TON 618 weighs 66 billion solar masses. It exceeds even the most optimistic Eddington limited growth predictions by factors of 6 to 60. According to our standard understanding of black hole physics and cosmic timelines, it should not exist, period. The universe simply had not been around long enough for it to grow this large through normal, physics-respecting feeding processes. Researchers have proposed multiple exotic theories attempting to explain this impossibility, each with significant problems. Perhaps TON 618 started much larger than a typical stellar mass black hole, instead of forming from a single massive star's death, the standard stellar collapse pathway producing black holes of 10 to 100 solar masses. Maybe it collapsed directly from a primordial gas cloud in the early universe, creating what's called a direct collapse black hole of thousands or millions of solar masses as its initial seed. The physics of direct collapse is complex and uncertain. For a gas cloud to collapse directly into a black hole rather than forming stars first, very specific conditions must be met. The gas must remain hot enough to avoid fragmenting into star-forming clumps, but dense enough to collapse under its own gravity. This requires suppressing normal cooling mechanisms, perhaps through intense radiation from nearby young galaxies preventing the gas from cooling, or through unusual chemical compositions lacking normal cooling elements. Computer simulation suggests these conditions were extremely rare even in the early universe. Getting a gas cloud massive enough to collapse directly into a million solar mass black hole requires such specific, finely tuned circumstances that it probably happened only occasionally. Whether it happened frequently enough to explain multiple objects like TON 618 remains hotly debated. Other researchers suggest TON 618 resulted from a cascade of black hole mergers, countless mergers of smaller black holes in an exceptionally dense star cluster during the universe's infancy. If hundreds of stellar mass black holes formed in close proximity and underwent repeated mergers, each merger combining masses additively, you could potentially build up to supermassive scales faster than through accretion alone. But this scenario requires an improbably long sequence of perfect encounters. Black holes are small targets. Even in dense star clusters, they're separated by light years. Getting them to merge requires that they somehow lose energy and angular momentum, causing their orbits to decay and spiral together. This typically happens through gravitational wave emission, a slow process, or through three-body interactions where a third object steals energy, bringing the black holes closer. Both mechanisms operate, but organising hundreds of successful mergers in the right sequence within 3 billion years strains plausibility. Additionally, mergers are violent events that produce powerful gravitational waves, ripples in space-time propagating at light speed. We've successfully detected gravitational waves from stellar mass black hole mergers using LIGO and Virgo detectors. A merger creating or substantially growing something like TON 618 would produce waves detectable across the universe, leaving imprints in the gravitational wave background. We haven't yet detected clear evidence of such ultra-massive mergers in the early universe, though our current instruments may lack sensitivity in the relevant frequency ranges. Some theorists propose super-Eddington accretion, the idea that under certain exotic conditions, black holes might feed faster than the Eddington limit normally allows. Perhaps in the dense, chaotic early universe, with higher gas densities and different environmental conditions, accretion rates could significantly exceed the classical Eddington limit. Mechanisms that might enable super-Eddington feeding include strong magnetic fields channeling matter through the radiation pressure barrier, geometrically thick accretion disks that trap radiation and prevent it from escaping to exert outward pressure, or rapid infall from multiple directions simultaneously, overwhelming the radiation feedback. Recent simulations suggest super-Eddington accretion might occur more commonly than previously thought, potentially boosting growth rates by factors of several to 10. But even generous super-Eddington scenarios struggle to produce 66 billion solar masses in 3 billion years. Starting from reasonable seed masses, you'd need sustained super-Eddington feeding at rates several times the classical limit, maintained continuously for billions of years, a scenario that seems physically implausible given feedback effects. The most uncomfortable and radical possibility is that our fundamental understanding of early universe conditions is incomplete or wrong. Perhaps matter was distributed very differently than current models predict. Maybe the first galaxies were substantially more compact and gas-rich, funneling material towards central black holes far more efficiently. Perhaps physical constants or laws operated slightly differently when the universe was younger, hotter, and denser. A disturbing idea that would require rewriting fundamental physics, but cannot be entirely excluded. Dark matter adds another layer of mystery and possibility. We know dark matter exists from its gravitational effects on galaxy rotation, gravitational lensing, and large-scale structure formation. But we don't know what dark matter actually is, what particles compose it, how it interacts with normal matter beyond gravity. Some exotic theoretical models propose interactions between dark matter and normal matter that could dramatically enhance black hole growth in the early universe through mechanisms that don't operate today or operate too weakly to detect. Whatever the true explanation, and it might involve a combination of several factors, TON 618 fundamentally challenges our understanding of cosmic evolution. It represents a phase of the universe we barely comprehend, a period when conditions were so different from today that our comfortable models fail. The early cosmos was apparently wilder, more violent, more rapidly evolving than we predicted. Massive structures coalesced faster than they should have. The rules governing cosmic architecture needed rewriting. The discovery of TON 618 and other similar ultramassive early black holes has sparked a minor revolution in cosmology, forcing theorists to reconsider the first 3 billion years of universal history. How did the first black holes form? How quickly could they grow? What role did they play in galaxy formation and cosmic structure development? These fundamental questions remain open, actively researched, far from settled. And TON 618 didn't form in isolation in empty space. It sits at the heart of a distant galaxy, a collection of billions of stars trapped in its immense gravitational grip, orbiting the monster at the centre. The incomprehensible scale, picture our sun hanging in space. That ball of fusion measures 864,000 miles across, about 109 times Earth's diameter. Light takes 8 minutes to reach Earth from its surface, travelling at 186,000 miles per second, cross 93 million miles of void. Our Sun is already incomprehensibly large by human standards. You could fit 1.3 million Earths inside it. Now multiply that Sun by 66 billion. That's the mass crushed into the singularity at TON 618's heart. But mass alone doesn't capture the scale. Black holes concentrate their mass into impossibly small points. The singularity itself has no volume in the conventional sense. The real measure of a black hole's physical size is its event horizon, the boundary where escape becomes impossible, where even light cannot break free. For TON 618, that boundary sits 40 billion miles from the centre, defining a sphere of no return so vast it challenges comprehension. Our entire solar system from Mercury to Neptune spans about 5.6 billion miles from edge to edge. Neptune, the outermost major planet, orbits roughly 2.8 billion miles from the Sun. That's 30 times Earth's distance, a voyage that took Voyager 212 years to complete. The event horizon of TON 618 stretches 14 times farther than Neptune's entire orbital path around our Sun. Visualize this carefully. Place our Sun where TON 618's singularity hides at the centre of this cosmic sphere. Mercury, with its tight 36 million mile orbit, would sit deep inside the event horizon, long since consumed and crushed beyond recognition. Venus, at 67 million miles, inside. Earth at 93 million miles, inside. Mars at 142 million miles, inside. The entire inner solar system, where all the rocky planets orbit, would be gone, swallowed by the forbidden zone. Jupiter, the gas giant orbiting at 484 million miles, inside the event horizon. Saturn with its magnificent rings at 886 million miles, inside. Uranus at 1.8 billion miles, inside. Neptune at 2.8 billion miles, taking 165 years to complete a single orbit around our Sun, inside. You could place 14 complete copies of Neptune's orbit, 14 full solar systems from Sun to Neptune, inside TON 618's boundary, and still have room left over. Voyager 1, humanity's most distant object, has been travelling away from the Sun since 1977 at about 38,000 miles per hour. It currently sits approximately 14.7 billion miles away in interstellar space, well beyond the Sun's influence, in the realm between stars. It's the farthest human-made object, our most distant emissary. If TON 618 replaced our Sun, Voyager 1, after 47 years of flight away from home, would still be inside the event horizon, falling inexorably toward oblivion with absolutely no hope of escape, no possibility of sending signals back, no chance of survival. The Kuiper Belt, where Pluto orbits along with thousands of icy bodies, extends from about 2.8 billion miles to 4.6 billion miles from the Sun. The entire Kuiper Belt would be inside TON 618's event horizon, the scattered disk, reaching perhaps 7.5 billion miles out, inside. Even the inner portions of the Oort cloud, that vast sphere of comets extending perhaps 15 billion miles from the Sun, would be within the point of no return. The scale becomes even more disturbing when you consider density and gravitational gradients. Our Sun is relatively diffuse despite its immense size. Its average density is about 1.4 grams per cubic centimetre, similar to honey or slightly denser than water. You could theoretically swim through parts of the Sun's interior if you could somehow survive the millions of degrees of heat. The Sun has volume, structure, layers. TON 618's event horizon encloses a volume millions of times larger than our Sun, yet all its mass, all 66 billion solar masses, crushes down to a single point smaller than an atom at the centre. This creates gravity gradients so extreme they defy human intuition. At the event horizon itself, gravity is strong enough to trap light, move inward even slightly, and the pull intensifies dramatically, space curves more severely, and escape becomes even more impossible, if such a thing can be measured in degrees. Move outward and space-time curves less severely. Gravity weakens, but the distance over which these changes occur spans cosmic scales. You could travel millions of miles closer to or farther from TON 618 and still measure significant detectable changes in gravitational field strength. Compare TON 618 to the black hole anchoring our own galaxy. Sagittarius, a star, the supermassive black hole around which our entire Milky Way orbits, weighs about 4 million solar masses, already an incomprehensible number. Its event horizon measures roughly 17 million miles across. You could fit the entire event horizon of Sagittarius A star comfortably inside Mercury's orbit, with room to spare on all sides. It's a massive object by any reasonable standard, holding 200 billion stars in gravitational thrall across the galactic disk. TON 618 weighs 16,500 times more than Sagittarius A star. Let that ratio sink in. Not 16 times, not 160 times, but 16,500 times more massive. If you placed both black holes side by side for comparison, Sagittarius A star would resemble a marble next to a cathedral. We orbit the marble, our entire civilization, every human who has ever lived, circling this marble at a comfortable distance of 26,000 light-years. TON 618 is the cathedral, vast, imposing, overwhelming in its scale. Consider what this means for any civilization unfortunate enough to exist near TON 618. Their entire understanding of astronomy, physics, and space itself would be warped by this object. Gravitational effects would dominate every measurement, every observation, every aspect of their existence. Time would flow at measurably different rates depending on which planet you measured it from. Clocks on inner worlds would tick noticeably slower than clocks on outer worlds. The tidal forces alone would constrain where planets could stably exist. Venture too close and tidal stress would literally pull planets apart. Our solar system feels safe, stable, predictable, because our sun is gentle by cosmic standards. We orbit at comfortable distances where gravity is strong enough to hold us in place but weak enough to allow stable, predictable orbits. Kepler's laws work beautifully. We can calculate planetary positions centuries in advance with extraordinary precision. The gravitational environment is calm, ordered, comprehensible. Near TON 618, no comfortable distance exists. The zone where planets could theoretically form and maintain stable orbits stretches across light years, distances where stars orbit rather than planets. And even there, at distances measured in light years from the event horizon, the black hole's influence would be inescapable. Orbital mechanics would be complex, chaotic, subject to perturbations from the central monster. Long-term orbital stability would be questionable. The night sky would be dominated by the blinding glare of the accretion disk if the black hole were actively feeding, making optical astronomy nearly impossible. Visualizing 40 billion miles challenges human cognitive capacity. Our brains didn't evolve to comprehend such distances. We evolved to track prey across kilometers, estimate distances to water sources measured in days of walking, judge throwing distances measured in meters. 40 billion miles is so far beyond our experiential range that it becomes meaningless without reference points. But understanding the scale matters profoundly because it reveals something deep about the nature of reality. Objects this large shouldn't exist, according to our carefully constructed models of how the universe works. Yet they do exist. We've detected them. We've measured them. We cannot ignore them or explain them away. And TON 618 isn't just big, it's massive enough to warp the very fabric of space-time around it in ways that challenge physics itself, creating phenomena that sound like science fiction, but are documented scientific fact. Which brings us to the edge, the event horizon, the ultimate boundary, the point where physics as we understand it begins to break down and reality becomes fundamentally strange, the point of no return. The event horizon isn't a physical surface. You cannot touch it, cannot see it directly, cannot detect it with any instrument. It exists only as a mathematical boundary, the distance from a black hole where escape velocity equals the speed of light. Cross that invisible line and the universe forbids your return. The laws of physics themselves make escape impossible. For TON 618, that line sits 40 billion miles from the singularity at the center. Light travels at 186,000 miles per second, 299,792 kilometers per second to be precise. Nothing in the universe travels faster. This isn't an engineering limitation or a technological barrier. It's a fundamental property of space-time itself. Light speed is the cosmic speed limit, woven into the fabric of reality by the structure of the universe. When gravity becomes strong enough to pull even light backward, preventing photons from escaping outward, no force in physics can overcome it. No hypothetical engine, no Exotic matter, no quantum trick can change this fact. Rocket engines become useless at the event horizon. Matter cannot accelerate to light speed. As you approach light speed, your mass effectively increases, requiring exponentially more energy to accelerate further. You can never quite reach that speed, let alone exceed it. Once you cross the event horizon, every direction in space points inward toward the singularity. Even moving away from the black hole still brings you closer to the center. Space itself has curved so severely that outward motion has become impossible. The event horizon's size depends entirely on mass. More mass generates stronger gravitational fields, which creates a larger region from which light cannot escape. The formula is elegantly simple. Take the mass, multiply by the gravitational constant, multiply by 2, divide by the speed of light squared. For TON 618, with its 66 billion solar masses, that calculation yields a radius of 40 billion miles. The Schwarzschild radius, named after Karl Schwarzschild, who first derived the solution to Einstein's field equations describing black holes. At that distance, space-time curvature becomes so severe that the geometry folds back on itself. Imagine a slope that gets progressively steeper and steeper. Normal slopes you can climb. Steep slopes become difficult. As the slope approaches vertical, climbing becomes impossible. You can maintain your position but cannot ascend. Now imagine the slope tilting past vertical, beyond 90 degrees, curving completely over until up points back down. That's what space-time geometry does at the event horizon. All paths lead down toward the singularity. The concept of away from the black hole loses meaning. Standing at TON 618's event horizon would feel deceptively normal, at least initially for a brief time. This is profoundly counterintuitive but mathematically certain. Gravity at that distance, despite being strong enough to trap light itself, wouldn't crush you instantly into a pancake. The black hole is so massive and the event horizon so immense that tidal forces, the difference in gravitational pull between your head and feet, spread out over enormous distances. The gradient is relatively gentle. You could cross the boundary without your body immediately realizing anything catastrophic had happened. This differs radically from smaller black holes. A stellar mass black hole formed from a collapsed star might have an event horizon only a few miles across, perhaps 10 or 20 kilometers in diameter. At that scale, tidal forces would be extreme. The difference in gravitational pull between your feet, closer to the center, and your head, farther away, would be so severe that you'd be torn apart, spaghettified, long before you reach the event horizon. Your body would stretch like taffy, bones would snap, molecules would separate. TON 618's immense size creates a fundamentally different experience. The curvature of space-time is extreme, but spread over such vast distances that the gradient becomes gentle. You could cross the boundary intact, conscious, perhaps not even aware initially that you'd passed the point of no return. You would have time, precious seconds or minutes to contemplate your fate, to understand what was happening. But make absolutely no mistake, once across that line, your fate is sealed with finality. Physics offers no loopholes, no escape clauses, no clever tricks. You cannot quantum tunnel your way out. The barrier isn't made of matter or energy, it's made of geometry itself. You cannot use wormholes, even if wormholes exist, which remains theoretical. Creating one requires exotic matter with negative energy density, which you don't have and cannot obtain. You cannot reverse time. Time flows in one direction, and inside the event horizon, all time-like paths point toward the singularity. The event horizon is absolute. It's the universe saying no with ultimate authority. What happens to matter crossing depends profoundly on your frame of reference, on whether you're the one falling in or observing from outside. This is one of relativity's most mind-bending consequences. From outside, someone watching you fall toward TON 618 would see something bizarre and disturbing. As you approach the event horizon, you would appear to slow down progressively. Your movements would become sluggish, as if you were moving through increasingly thick syrup. Your descent would decelerate, colours emanating from you, light reflecting off your body or from your rocket engines, would redshift toward darkness, shifting from blue to green to yellow to red to infrared to radio waves. Eventually, you would seem to freeze completely at the boundary, hovering there forever in a moment of eternal suspension. Your image would fade gradually, darkening over seconds or minutes as the photons carrying visual information about you redshift beyond detectability. You would become a ghost, a fading afterimage frozen at the edge of oblivion, and then vanish completely from view as all light from you stretches to infinite wavelength. This isn't optical illusion or measurement error. Time dilation near the event horizon is real, predicted by general relativity and confirmed by countless experiments and observations. From your perspective falling inward, you experience time normally. Your watch ticks at normal rate. Your thoughts proceed at normal speed. But from the perspective of someone far away in flat space-time, time for you has slowed dramatically. The closer you get to the event horizon, the more severe this effect becomes. At the boundary itself, time dilation approaches infinity. From the outside observer's reference frame, you never quite cross the horizon. You asymptotically approach it forever. From your perspective falling inward, the experience would be different but equally strange and disturbing. You would fall through the event horizon in finite measurable time, perhaps seconds, perhaps minutes, depending on your trajectory and velocity. Nothing would feel unusual about the crossing itself. No barrier, no sensation, no warning sign. Just a mathematical boundary in space-time that you pass through like crossing an invisible line painted on the ground. But the universe outside would appear to behave strangely. As you fell, you'd observe the cosmos beyond the black hole seeming to speed up. Stars would appear to age rapidly before your eyes. Their light would be blue-shifted, compressed to higher frequencies and energies. Planets would whip around their orbits faster and faster. Galaxies would spin, collide, merge. Billions of years of cosmic history would flash past in what feels to you like moments. You'd be watching the future unfold, seeing eons pass while you experience only minutes. Then you would cross over and everything would fundamentally change. The singularity would no longer exist as a point in space ahead of you, a destination you're travelling toward. It would become a moment in your future, an instant in time that you're hurtling toward inevitably. No matter which direction you accelerated your engines, no matter how you maneuvered, you would move closer to the singularity in time rather than space. The singularity isn't a place you can avoid by turning left or right, up or down. It's a when, not a where, as inevitable as next Tuesday, as inescapable as tomorrow morning. The event horizon of TON 618 encompasses a volume of space larger than most star systems, larger than the orbits of entire planetary families. Inside that volume, the normal rules of space-time cease functioning in any way we recognize. Cause and effect become tangled in ways quantum mechanics suggests but general relativity cannot fully describe. Directions lose their conventional meanings. The geometry of space itself has transformed into something alien, something that doesn't map onto human intuition or experience. And beyond that boundary, past the point of no return, something even stranger awaits. The singularity, the place where all the mass hides, where the mathematics produce infinities, where physics admits complete defeat and our theories break down entirely, when time becomes a weapon. Time isn't constant. It doesn't flow at the same rate everywhere in the universe. This isn't philosophy, metaphysics, or abstract theorizing. It's measured, documented fact. Atomic clocks on satellites orbiting Earth tick measurably faster than identical atomic clocks on Earth's surface. The difference is tiny, approximately 38 microseconds per day for GPS satellites, but real enough that GPS systems must account for it, or they would accumulate positioning errors of several kilometers per day. If engineers ignored relativistic time dilation, your phone's navigation would be useless. The effect occurs because gravity warps time. Satellites orbit high above Earth, where gravity is slightly weaker than at the surface. Time flows slightly faster there. This is gravitational time dilation, a prediction of Einstein's general relativity that's been verified in countless experiments with extraordinary precision. Near TON 618, time dilation stops being a subtle correction factor and becomes overwhelming, dominating every aspect of physics. A clock sitting just outside the event horizon, somehow suspended there by an impossibly powerful engine, would tick dramatically slower than a clock far away in deep space, far from any massive objects. The closer you approach the event horizon, the more severe the effect becomes, accelerating toward infinity. At the event horizon itself, time dilation becomes infinite. Time, from the perspective of a distant observer, stops completely. Einstein's general relativity explains why this happens. Mass curves space-time, not just space, but the unified four-dimensional fabric of space and time together. The more mass concentrated in a region, the more severe the curvature. Time is an integral part of that geometry. When space bends dramatically under extreme gravity, time bends with it, stretching like taffy. Gravity doesn't just pull objects together across space, it literally stretches the flow of time, making clocks run slower, making processes unfold more gradually when observed from outside the gravitational field. Imagine two observers, both with perfect synchronized atomic watches. One stays far from TON 618, safely positioned in flat space-time billions of miles from the monster. The other descends toward the black hole in a spacecraft equipped with powerful engines, stopping at various distances to measure time dilation effects and report back. At 1 billion miles out from the event horizon, still vastly far away, the difference would be noticeable but relatively small. The descending observer's watch might lose a few seconds per hour compared to the distant observer's watch. Subtle, but measurable with precision instruments. At 100 million miles from the event horizon, the gap widens significantly. The descending observer's watch now loses minutes per hour. Time is flowing noticeably slower for them. Communications with a distant observer become strained. Radio signals take longer to arrive from the distant observer's perspective because time is flowing differently. At 10 million miles from the event horizon, the effect becomes dramatic. The descending observer's watch loses hours per day compared to the distant observer. What feels like 24 hours of passing time for the person near the black hole corresponds to several days for the person far away. As the descending observer approaches 40 billion miles, the event horizon boundary itself, the effect explodes exponentially. Every second that passes for them corresponds to thousands of seconds for the distant observer, then millions, then billions, then trillions. The ratio approaches infinity. Time, for the person near the event horizon, essentially stops from the perspective of anyone far away. They become frozen in time, aging infinitesimally slowly, their watch ticking at a rate approaching zero. From the perspective of the person falling in, nothing seems wrong or unusual. Their watch ticks normally, 1 second per second by their measurement. Their heartbeat feels regular, approximately 60 beats per minute. Their thoughts proceed at normal human speed. The laws of physics in their immediate vicinity appear unchanged. But if they could somehow look back at the universe they left behind, they would see it speeding up like watching video on fast-forward at increasing rates. Stars would live and die in moments. Planets would whip around their orbits. Galaxies would spin, collide, merge, and separate. The entire future history of the cosmos would play out before their eyes in subjective minutes. This creates a profound and tragic paradox for any civilization attempting to study TON 618 up close. Send a probe to the event horizon with instructions to take measurements and return data, and mission control could wait millions or billions of years for that data to arrive. What feels like a few hours of observation time for the probe, hours during which its instruments collect invaluable measurements of the extreme environment, translates to geological epochs of waiting time for everyone else. The probe crew would return to find their civilization extinct, their star system altered beyond recognition, perhaps even their galaxy transformed by billions of years of evolution. Long-duration missions become not just impractical, but physically impossible. Even brief observations take longer than civilization survive, longer than stars shine, longer than meaningful timescales in the universe. The time dilation creates an impassable barrier not of distance, but of time itself. Time dilation also affects how we observe the accretion disk around TON 618. Matter spiraling inward experiences different rates of time depending on distance from the event horizon. The inner edge of the disk, closest to the point of no return, moves through time much slower than the outer edge, located farther away where gravity is weaker. This creates strange visual effects that distort our observations. Light emitted from the inner disk gets severely redshifted, stretched to longer wavelengths, because it must climb out of the deep gravitational well where time flows slowly. Blue light emitted from hot plasma near the event horizon might reach us as red light or even infrared radiation. The disk appears warped, distorted, with colours and brightness varying not just by temperature and density, but by position in the gravitational field. Modelling the disk requires accounting for these relativistic effects, making interpretation of observations highly complex. Gravity also bends light paths in extreme ways near TON 618. Photons travelling near the black hole don't follow straight lines, they follow curved trajectories through warped spacetime. Light rays that would normally miss your eye entirely can be bent around the black hole and reach you from unexpected directions. This means you can see multiple images of the same object, distorted and displaced. Light from a star located behind the black hole might curve around both the left and right side simultaneously, reaching your eyes from two different directions. You see two images of the star, one on each side of the black hole, even though there's only one actual star. Move to a slightly different position, and the images shift, merge, separate, creating complex lensing patterns. Close enough to the event horizon, light can orbit the black hole in circular or spiral paths before either falling in or escaping. This creates a region called the photon sphere, located at 1.5 times the event horizon radius. For TON 618, that's 60 billion miles from centre. Any light entering this zone either falls toward the event horizon or escapes to infinity, but some photons circle the black hole multiple times before deciding their fate. In the photon sphere, you could theoretically see the back of your own head if you positioned yourself precisely. Photons leaving the back of your skull would curve completely around the black hole following curved spacetime and enter your eyes from the front. You'd see yourself from behind, creating impossible visual recursions. The photon sphere represents one of the strangest geometric consequences of extreme spacetime curvature. Time dilation near TON 618 reveals something profound and unsettling about black holes. They aren't just massive objects sitting in space like unusually heavy planets or stars. They're regions where space and time become so severely deformed that our normal concepts lose meaning entirely. The event horizon isn't just a boundary in space separating inside from outside. It's a boundary in time itself, separating the universe we know and understand from something fundamentally different and alien. And here's perhaps the most disturbing aspect of all this. Every black hole does this. Stellar mass black holes weighing just a few times our sun's mass warp time. Intermediate black holes weighing thousands of solar masses warp it more. Supermassive black holes at galaxy centers warp it dramatically. But TON 618, with its 66 billion solar masses, warps time on a scale affecting volumes of space larger than entire solar systems. The distortion extends across billions of miles. You would feel measurable time dilation effects long before you could see the event horizon itself, long before any visible sign of danger. This makes TON 618 not just the most massive black hole we've discovered, but the largest time machine in the known universe. It creates temporal gradients so steep that moving a few million miles closer to or farther from the event horizon changes how fast you age relative to the rest of the universe. It's a cosmic object that weaponizes time itself, using relativistic physics to create an environment where time becomes variable, negotiable, fundamentally strange. And at its heart, at the very center where the singularity waits in mathematical certainty, time may cease to exist entirely in any way we could recognize or describe. The flow of time might stop, reverse, become meaningless. We simply don't know. Our mathematics breaks down, our physics reaches its limits, and we're left with profound mysteries. But the black hole itself is completely dark and invisible. What makes TON 618 detectable from 10 billion light-years away? What allows us to study it at all is what surrounds it. The accretion disk, the spiral of doomed matter, the maelstrom of dying material shining brighter than 400 trillion stars combined. The maelstrom of annihilation. The black hole at TON 618 center emits absolutely no light. By definition, light cannot escape from within the event horizon. What we observe when we point our telescopes at TON 618, what produces the overwhelming luminosity we measure, is matter dying as it falls toward oblivion. That dying matter, that doomed material spiraling inward toward inevitable destruction, outshines 400 trillion suns. It blazes with more light than thousands of entire galaxies combined. An accretion disk forms because infalling matter has angular momentum, the rotational equivalent of linear momentum, the tendency of spinning things to keep spinning. Objects falling toward a gravitational center don't drop straight down like a stone falling toward Earth. They spiral inward like water circling a drain, maintaining their angular momentum as they descend. The spiral flattens into a disk structure due to countless collisions between particles. When particles with random velocities collide, they average out their motions. Eventually, everything settles into the same plane, rotating in the same direction, forming a flat disk structure that resembles a cosmic hurricane viewed from above. For TON 618, this disk is enormous in scale, almost incomprehensibly vast. It stretches across light years of space, distances so large that light itself takes years to traverse from one edge to the other. Gas, dust, fragments of shredded stars and all manner of materials swirl inward at velocities approaching the speed of light. The inner edge hovers just beyond the event horizon, at the innermost stable circular orbit, where matter can exist before plunging irreversibly inward. The outer edge extends far enough that planets could theoretically orbit within it, if any somehow survived the violent formation process. Friction generates tremendous heat throughout the disk. As particles collide and rub against each other at high velocities, they transfer kinetic energy. That energy converts to heat through viscous interactions. Temperature rises progressively as you move inward toward the center. The inner regions of the disk, moving fastest and experiencing the most intense friction and gravitational compression, heat to billions of degrees Kelvin. Matter at these temperatures doesn't just glow like a hot coal, it doesn't simply emit light. It screams electromagnetic radiation across the entire spectrum with terrifying intensity. The disk emits X-rays from the hottest regions, ultraviolet light from slightly cooler areas, visible light, infrared radiation from the outer cooler regions, and radio waves from the most distant parts, simultaneously, all wavelengths at once, creating a composite signal we can detect and analyze from Earth. If you could somehow survive near TON 618 and see the accretion disk with human eyes, an impossible hypothetical, but useful for visualization, it would appear as a blindingly bright ring surrounding an invisible center. The black hole itself would be a perfect circle of absolute darkness, blacker than the blackest night, outlined by the brilliant disk. Colors would shift dramatically depending on radial distance from center. The outermost regions might glow dull red, with temperatures of thousands of degrees. Moving inward, orange, then yellow, then white, then blue, becoming progressively more intense. The innermost regions would shine with blue-white brilliance so intense that looking directly at it would instantly burn retinas and cause permanent blindness. But the disk doesn't just emit light normally, it emits more light than should be physically possible from such a relatively small region of space. TON 618's accretion disk reaches 400 trillion times the luminous output of our Sun. To put that in perspective, pack together all the light from every star in the Milky Way galaxy, all 200 billion stars, from tiny red dwarfs to massive blue giants, and TON 618 still outshines the entire collection by a factor of thousands. It's not even close. Consider Andromeda, our nearest major galactic neighbour, containing approximately 1 trillion stars. TON 618 outshines Andromeda by a factor of 400. Even massive galaxy clusters containing hundreds of individual galaxies, with their combined trillions upon trillions of stars, can be dimmer than this single object, this single accretion disk around one black hole. This extreme brightness is what defines TON 618 as a quasar, quasi-stellar radio source, the term coined by early astronomers. Quasars represent the brightest sustained objects in the universe, active galactic nuclei powered by supermassive black holes consuming vast amounts of material. They're so luminous they can be detected across billions of light years, allowing us to study them despite their enormous distances. Early astronomers, seeing point-like sources of immense brightness, thought they were strange stars relatively nearby. Only later, when redshift measurements revealed their true distances, did we understand they were feeding black holes billions of light years away, so bright they remain visible across cosmic expanses. The amount of matter TON 618 must consume to maintain this brightness is staggering beyond normal comprehension. Calculations based on luminosity and accretion physics suggest it consumes roughly 10 solar masses of material every year. 10 times our Sun's entire mass, spiraling past the event horizon annually. That's equivalent to consuming a star the mass of our Sun every 36 days. Over millions of years, that appetite adds up to billions of solar masses consumed, vanished forever, beyond the point of no return. The disk isn't uniform or smooth. It has complex structure, variations, features. Hotspots form where density increases due to instabilities, or the infall of particularly large chunks of matter. Magnetic fields thread through the ionized plasma, creating loops, filaments, and complex topological structures. Turbulence causes fluctuations in brightness that we can observe and measure. Sometimes TON 618 flares brighter, perhaps when a particularly dense gas cloud falls in, or a star wanders too close and gets disrupted. Sometimes it dims slightly, perhaps when feeding slows temporarily. These variations happen over timescales of months or years, fast enough that we can observe changes within single human lifetimes despite the 10 billion light-year distance. The accretion disk also serves as a natural particle accelerator, one of the most powerful in the universe. Magnetic fields in the superheated plasma trap charged particles, electrons, protons, ionized atoms, and whip them to near-light speed through electromagnetic forces. These particles spiral along magnetic field lines, accelerating continuously, emitting synchrotron radiation as they do so. The energies involved are absurd by terrestrial standards. Individual electrons in TON 618's accretion disk carry energies higher than anything we can produce in our most powerful particle accelerators on Earth, higher than CERN's Large Hadron Collider can achieve even in its most successful collisions. Temperatures in the inner accretion disk reach several billion degrees Kelvin, let's say 2 to 3 billion degrees, in the hottest regions closest to the event horizon. For comparison and context, our Sun's core, where nuclear fusion occurs, sits at approximately 15 million degrees Celsius, call it 15 million Kelvin. Our Sun's surface, the photosphere we see, measures about 6,000 Kelvin. Matter in TON 618's accretion disk is hundreds of thousands of times hotter than the Sun's surface and hundreds of times hotter than the Sun's core, where fusion reactions generate all the energy that makes life on Earth possible. Nothing solid can exist at temperatures of billions of degrees. Molecules break apart instantly, atoms disintegrate into their constituent particles. Electrons strip completely away from nuclei, leaving bare protons and atomic nuclei surrounded by a sea of free electrons. Matter becomes plasma, the fourth state of matter beyond solid, liquid, and gas. This plasma is completely ionized, every atom separated into charged particles, creating a soup of electrons and nuclei moving at relativistic speeds, held together only by gravity and powerful magnetic fields. The disk isn't a solid structure despite being called the disk. It's a maelstrom of ionized gas, a storm of plasma and magnetic fields, a region where matter exists in its most extreme state before crossing the event horizon and vanishing forever. The disk churns and roils with turbulence, with shock waves propagating through it, with magnetic reconnection, events releasing sudden bursts of energy. And from this chaos, from this violent maelstrom of dying matter, something even more extreme emerges: jets. Massive fountains of matter and energy shoot outward from the poles of TON 618, perpendicular to the accretion disk, reaching speeds that approach the ultimate cosmic limit. These jets stretch for thousands of light years across space, carving tunnels through the intergalactic medium like cosmic blowtorches of unimaginable power. The cosmic blowtorch perpendicular to the accretion disk, twin jets of matter blast outward from TON 618's poles at 99% the speed of light. These jets stretch for thousands of light years across intergalactic space, carving tunnels through the cosmic medium and ploughing into surrounding gas clouds like cosmic fire hoses, powered by energies that dwarf anything we can comprehend. Jets form through an intricate process involving magnetic fields, rotation, and the extreme physics near the event horizon. As the accretion disk spins around the black hole, it drags magnetic field lines with it through a process called frame dragging. The black hole's rotation twists spacetime itself, and magnetic fields embedded in the plasma get pulled along, wrapping around the black hole's rotational axis like thread winding around a spool. These magnetic field lines twist and spiral, becoming increasingly concentrated near the poles. Charged particles in the accretion disk, electrons, protons, ionized, atoms, get caught in these spiraling magnetic fields. The fields act like rails or guides, channeling particles along specific paths. Once captured, Particles accelerate continuously along these magnetic highways, gaining energy from the rotation of the disk, from magnetic reconnection events, and from the twisting magnetic field geometry itself. Think of it as nature's most powerful railgun or particle accelerator. The magnetic fields provide the accelerating structure. Particles ride those magnetic field lines outward, continuously gaining speed and energy. By the time they shoot free from the immediate vicinity of the black hole, escaping the inner accretion disk region, they're moving at relativistic speeds, substantial fractions of light speed. The fastest particles in the jets reach 99% of light speed or even higher. The material in jets isn't solid matter, isn't even ordinary gas, it's plasma, a superheated, completely ionized mixture of electrons, protons, and other subatomic particles, all moving at tremendous velocities. These particles carry extraordinary energy. Individual electrons in TON 618's jets have energies millions of times higher than anything achievable in human-built particle accelerators. They're cosmic rays, among the most energetic particles in the entire universe. The jets are remarkably narrow and collimated, only a few light years across at their base near the black hole, maintaining coherent structure across thousands of light years of travel. Somehow, despite the distances involved, magnetic fields keep the jets confined, preventing them from spreading out and dissipating into the surrounding space. This collimation is one of astrophysics' enduring mysteries. The exact physics that maintains jet coherence over such vast scales remains actively debated. Various mechanisms have been proposed: magnetic pinching, where the magnetic field squeezes the jet inward like a magnetic nozzle, internal shock structures that help confine the flow, or rotation creating centrifugal barriers. When these jets slam into surrounding gas clouds and intergalactic medium, they create powerful shock waves. The collision is violent, sudden, catastrophic. The shock waves heat ambient gas to millions of degrees almost instantaneously, stripping electrons from atoms and creating expanding bubbles of hot, X-ray emitting plasma. These shocks also generate intense radio emissions through synchrotron radiation. Charged particles spiraling in magnetic fields produce radio waves we can detect from Earth, even across billions of light years. TON 618's jets are so phenomenally powerful that they excavate giant cavities in the intergalactic medium. Enormous bubbles or lobes of space hundreds of thousands of light years across, where normal gas has been completely blown away, evacuated by the relentless pressure of the jets. These regions appear as voids in X-ray observations, surrounded by shells of compressed heated gas. The jets have literally reshaped the environment on scales comparable to entire galaxies. The energy carried by these jets is staggering beyond easy comprehension. Conservative estimates suggest TON 618's jets contain as much kinetic energy as the light emitted by millions of entire galaxies combined. They inject energy into the cosmos at rates that can fundamentally affect galaxy formation across vast regions of space. Gas that might otherwise cool, collapse, and form new generations of stars gets heated and dispersed by jet impacts, remaining too hot to condense. This energy injection can suppress star formation across volumes spanning megaparsecs, millions of light years. This phenomenon represents what astronomers call AGN feedback, active galactic nucleus feedback. Supermassive black holes don't exist in isolation, passively consuming whatever matter randomly falls their way. They actively regulate their own growth and profoundly influence the evolution of their host galaxies and surroundings. When a black hole feeds vigorously, creating a luminous quasar, the resulting jets and intense radiation blow away surrounding gas in a violent outburst. This feedback mechanism starves the galaxy of raw material needed for continued star formation. New stars cannot form without cool, dense gas clouds to collapse. When jets and radiation heat and expel this gas, star formation drops dramatically or ceases entirely. The feedback also starves the black hole itself of additional fuel. Without fresh gas falling inward, the accretion disk thins, luminosity drops, the jets weaken. Overcosmic, timescales spanning millions or billions of years. This feedback mechanism may explain why black holes don't grow indefinitely, to consume everything around them. TON 618 is already extraordinarily massive, but it cannot keep feeding forever. Eventually, whether in the past or future, it exhausts nearby gas supplies or blows them away so effectively that accretion slows to a trickle. The accretion disk fades. The jets shut down. The quasar goes dark, leaving only the massive but invisible black hole behind. But while jets remain active, they rank among the most violent and energetic phenomena in the entire universe. The particles streaming through those jets carry enough energy to strip electrons from atoms across vast distances, ionize gas clouds light years away, and trigger cascading shock waves. Anything caught directly in a jet's path would be annihilated instantly, not just destroyed, but broken down to constituent particles by the overwhelming energy flux. Even at distances of thousands of light years from TON 618, at regions where the jets have spread and weakened substantially, they remain dangerous to any hypothetical nearby systems. The radiation environment would be harsh, inhospitable to life as we know it. High-energy particles would rain down continuously, sterilizing planetary surfaces and stripping away atmospheres. Jet orientation matters critically for observation. TON 618's jets point away from Earth rather than toward us. We observe the black hole from an angle, viewing the accretion disk somewhat edge-on. This is fortunate for our observations. If the jets were pointed directly at Earth, TON 618 would appear even brighter, possibly by factors of 10 or more, and would fall into a special category called blazars. Blazars are quasars with jets aimed directly at observers. When you're looking straight down the barrel of a relativistic jet, relativistic beaming effects concentrate the radiation into a narrow cone pointing toward you, dramatically amplifying the apparent brightness. Blazars are the brightest persistent objects we can observe, varying wildly in brightness as features in the jet move and evolve. Fortunately, TON 618 is not a blazar. We're spared the full brunt of its power. But even from our sideways view, the jets remain detectable. Radio telescopes pick up strong emissions from the regions where jets interact with surrounding matter. X-ray satellites detect the hot gas in the jet lobes. These observations across multiple wavelengths reveal jet structure, composition, speed, and energy content, allowing us to reconstruct the three-dimensional geometry of this cosmic fountain. The jets also serve as compelling evidence for TON 618's rotation. Only rotating black holes, what physicists call Kerr black holes, can efficiently produce jets this powerful. Non-rotating black holes, called Schwarzschild black holes, have much weaker jet production. Rotation stores enormous energy in the twisted space-time, geometry around the event horizon, a region called the ergosphere where space-time itself rotates with the black hole. Magnetic fields can tap into this rotational energy reservoir and channel it into the jets through the Blanford-Zizek mechanism, named after the physicists who described it. This means TON 618 isn't just sitting passively in space, it's spinning, potentially at high velocity, dragging space-time with it like a massive whirlpool. The rotation adds angular momentum to the jets, helps collimate them, and provides the energy that drives them to such extreme velocities across such enormous distances. And this massive, spinning, feeding black hole appeared impossibly early in cosmic history, presenting one of cosmology's most profound unsolved mysteries. The timeline that shouldn't exist. TON 618 existed when the universe was less than 3 billion years old, meaning the light we observe today left this object during the universe's infancy. To put this in proper perspective, the universe is currently 13.8 billion years old. TON 618 had already grown to 66 billion solar masses in less than a quarter of the cosmos's total lifetime, less than 22% of the universe's current age. According to everything we understand about black hole physics, growth rates, and cosmic evolution, this should be completely impossible. It violates our carefully constructed models of how supermassive black holes form and grow. Black holes grow primarily by consuming matter through accretion. Gas falls in, dust spirals inward, stars wander too close and get shredded. Each addition adds incrementally to the black hole's mass. But there are strict physical limits governing how fast this process can occur, limits imposed by the fundamental laws of physics, not by engineering constraints or technological barriers. This constraint is called the Eddington limit, named after British astrophysicist Arthur Eddington, who first described it mathematically in the early 20th century. The physics is straightforward but profound. When matter falls toward a black hole and accelerates under intense gravity, it gets compressed and heated through friction and collisions. This heating produces intense radiation, light, X-rays, all forms of electromagnetic energy. That radiation exerts outward pressure on any additional matter trying to fall inward. Photons carry momentum, they push on things. Eventually, if enough matter is falling in and producing enough radiation, the outward radiation pressure precisely balances the inward gravitational pull. At this equilibrium point, called the Eddington limit, matter cannot physically fall in any faster. Additional material gets blown away by radiation pressure before it can cross the event horizon. The black hole has reached its maximum sustainable feeding rate for its current mass. This creates a fundamental speed limit on black hole growth, an absolute ceiling on how fast mass can be added. The Eddington limit isn't negotiable or avoidable. It's a direct consequence of radiation pressure opposing gravity. For a black hole feeding continuously at the Eddington limit without interruption, physicists can calculate precisely how quickly it can grow. The growth is exponential. The black hole doubles its mass every roughly 50 million years when feeding at maximum rate. Starting from a stellar mass black hole formed from a massive star's supernova, perhaps 10 to 100 times the Sun's mass, and feeding continuously at the Eddington limit for 3 billion years, you reach approximately 1 billion solar masses. Maybe you could stretch to 10 billion solar masses if you pushed every assumption to its absolute breaking point. Assumed perfect conditions, perfect efficiency, perfect continuous feeding without any interruptions. TON 618 weighs 66 billion solar masses. It exceeds even the most optimistic Eddington limited growth predictions by factors of 6 to 60. According to our standard understanding of black hole physics and cosmic timelines, it should not exist. Period. The universe simply had not been around long enough for it to grow this large through normal, physics-respecting feeding processes. Researchers have proposed multiple exotic theories attempting to explain this impossibility, each with significant problems. Perhaps TON 618 started much larger than a typical stellar mass black hole. Instead of forming from a single massive star's death, the standard stellar collapse pathway producing black holes of 10 to 100 solar masses, maybe it collapsed directly from a primordial gas cloud in the early universe, creating what's called a direct collapse black hole of thousands or millions of solar masses as its initial seed. The physics of direct collapse is complex and uncertain. For a gas cloud to collapse directly into a black hole rather than forming stars first, very specific conditions must be met. The gas must remain hot enough to avoid fragmenting into star-forming clumps, but dense enough to collapse under its own gravity. This requires suppressing normal cooling mechanisms, perhaps through intense radiation from nearby young galaxies preventing the gas from cooling, or through unusual chemical compositions lacking normal cooling elements. Computer simulations suggest these conditions were extremely rare even in the early universe. Getting a gas cloud massive enough to collapse directly into a million solar mass black hole requires such specific, finely tuned circumstances that it probably happened only occasionally. Whether it happened frequently enough to explain multiple objects like TON 618 remains hotly debated. Other researchers suggest TON 618 resulted from a cascade of black hole mergers, countless mergers of smaller black holes in an exceptionally dense star, clustered during the universe's infancy. If hundreds of stellar mass black holes formed in close proximity and underwent repeated mergers, each merger combining masses additively, you could potentially build up to supermassive scales faster than through accretion alone. But this scenario requires an improbably long sequence of perfect encounters. Black holes are small targets. Even in dense star clusters, they're separated by light years. Getting them to merge requires that they somehow lose energy and angular momentum, causing their orbits to decay and spiral together. This typically happens through gravitational wave emission, a slow process, or through three-body interactions where a third object steals energy, bringing the black holes closer. Both mechanisms operate, but organizing hundreds of successful mergers in the right sequence within 3 billion years strains plausibility. Additionally, mergers are violent events that produce powerful gravitational waves, ripples in, space-time propagating at light speed. We've successfully detected gravitational waves from stellar mass black hole mergers using LIGO and Virgo detectors. A merger creating or substantially growing something like TON 618 would produce waves detectable across the universe, leaving imprints in the gravitational wave background. We haven't yet detected clear evidence of such ultra-massive mergers in the early universe, though our current instruments may lack sensitivity in the relevant frequency ranges. Some theorists propose super-Eddington accretion, the idea that under certain exotic conditions, black holes might feed faster than the Eddington limit normally allows. Perhaps in the dense, chaotic early universe, with higher gas densities and different environmental conditions, accretion rates could significantly exceed the classical Eddington limit. Mechanisms that might enable super-Eddington feeding include strong magnetic fields channeling matter through the radiation pressure barrier, geometrically thick accretion disks that trap radiation and prevent it from escaping to exert outward pressure, or rapid infall from multiple directions simultaneously, overwhelming the radiation feedback. Recent simulations suggest super-Eddington accretion might occur more commonly than previously thought, potentially boosting growth rates by factors of several to 10. But even generous super-Eddington scenarios struggle to produce 66 billion solar masses in 3 billion years starting from reasonable seed masses. You'd need sustained super-Eddington feeding at rates several times the classical limit, maintained continuously for billions of years, a scenario that seems physically implausible given feedback effects. The most uncomfortable and radical possibility is that our fundamental understanding of early universe conditions is incomplete or wrong. Perhaps matter was distributed very differently than current models predict. Maybe the first galaxies were substantially more compact and gas-rich, funneling material towards central black holes far more efficiently. Perhaps physical constants or laws operated slightly differently when the universe was younger, hotter, and denser. A disturbing idea that would require rewriting fundamental physics but cannot be entirely excluded. Dark matter adds another layer of mystery and possibility. We know dark matter exists from its gravitational effects on galaxy rotation, gravitational lensing, and large-scale structure formation. But we don't know what dark matter actually is, what particles compose it, how it interacts with normal matter beyond gravity. Some exotic theoretical models propose interactions between dark matter and normal matter that could dramatically enhance black hole growth in the early universe through mechanisms that don't operate today or operate too weakly to detect. Whatever the true explanation, and it might involve a combination of several factors, TON 618 fundamentally challenges our understanding of cosmic evolution. It represents a phase of the universe we barely comprehend, a period when conditions were so different from today that our comfortable models fail. The early cosmos was apparently wilder, more violent, more rapidly evolving than we predicted. Massive structures coalesced, faster than they should have. The rules governing cosmic architecture needed rewriting. The discovery of TON 618 and other similar ultramassive early black holes has sparked a minor revolution in cosmology, forcing theorists to reconsider the first 3 billion years of universal history. How did the first black holes form? How quickly could they grow? What role did they play in galaxy formation and cosmic structure development? These fundamental questions remain open, actively researched, far from settled. And TON 618 didn't form in isolation in empty space. It sits at the heart of a distant galaxy, a collection of billions of stars trapped in its immense gravitational grip, orbiting the monster at the centre. The galaxy in the shadow, TON 618, doesn't float alone in the cosmic void. It anchors a galaxy, a massive collection of billions of stars, gas clouds, dust and dark matter, all bound together gravitationally and orbiting the supermassive black hole at the centre. Those stars circle the monster at various distances, never getting close enough to be consumed directly, but forever held in gravitational thrall, their entire existence dominated by the presence of this central leviathan. The galaxy itself proves extremely difficult to observe directly and study in detail. The quasar at its core, the blindingly bright accretion disk, outshines everything else by such overwhelming margins that resolving the galaxy's structure becomes nearly impossible with current technology. Imagine trying to spot a candle flame while staring directly at an industrial searchlight pointed at your eyes, or attempting to see stars during broad daylight. The quasar's glare swamps everything, drowning out the collective light from billions of stars in pure luminous intensity. Telescopes struggle to image the galaxy through this overwhelming brightness. Even our most advanced instruments equipped with coronagraphs and sophisticated image processing techniques barely resolve structural details. The stars emit light, certainly, billions of them, each contributing, but their combined output represents a tiny fraction of the blinding glare from the central accretion disk. We see TON 618 primarily as a point source, a brilliant dot with only the faintest hints of the surrounding galaxy. What we can determine through indirect methods is that the galaxy must be absolutely massive. Black holes and their host galaxies follow observable relationships discovered through studies of thousands of nearby galaxies. Bigger galaxies tend to harbour bigger central black holes. The correlation isn't perfect, there's scatter in the relationship, but it's strong and well established statistically. A black hole as massive as TON 618, weighing 66 billion solar masses, almost certainly sits in a galaxy weighing trillions of solar masses, a truly enormous galaxy by any standard. Stars in that galaxy live under bizarre and extreme conditions compared to our comfortable solar neighbourhood. The gravitational influence of TON 618 extends across light years from the centre. Stars in the inner regions within the sphere of influence we'll discuss later orbit at tremendous velocities, thousands or tens of thousands of kilometres per second. Their orbits are fast and often chaotic, subject to perturbations from other stars and the overwhelming central mass. These high-velocity orbits lead to frequent close encounters between stars. In our galaxy, stellar collisions are extraordinarily rare. Stars are tiny targets separated by vast distances, even in relatively dense regions. But in the core of TON 618's host galaxy, where stellar density is extreme and velocities are high, collisions or near misses occur far more frequently. Some stars get flung outward at high speeds, becoming hypervelocity stars ejected from the galaxy entirely. Others get sent on plunging orbits toward the black hole itself, doomed to eventual tidal disruption. Any planetary systems in that galaxy would face existential challenges unknown in our relatively calm Milky Way. Gravitational perturbations from the massive black hole and from frequent close stellar passages would destabilize planetary orbits over relatively short timescales. Planets could be ejected from their star systems entirely, becoming rogue planets drifting in interstellar space. Others might be sent crashing into their host stars or perturbed into highly eccentric orbits alternating between freezing cold and roasting heat. Long-term orbital stability, the predictability that allows life to evolve on Earth over billions of years, would be questionable or absent. Climate stability would be compromised, the night sky would be crowded with stars far brighter and more numerous than Earth's sky. Beautiful but indicative of the dangerous environment, the radiation environment would be punishing and likely lethal to most life forms. If TON 618 is actively feeding, as it appears to be in the snapshot we observe, the accretion disk and jets flood the entire galaxy with high-energy particles, X-rays and gamma rays. This radiation would bathe planets throughout the galaxy, not just in the immediate core region. X-rays and gamma rays are ionizing radiation. They strip electrons from atoms, break chemical bonds, damage DNA, and destroy complex organic molecules necessary for life. Planetary atmospheres would be stripped away gradually by this radiation assault. Even worlds orbiting far from the galactic center, seemingly at safe distances, would receive dangerous doses. Only planets with exceptionally strong magnetic fields might maintain atmospheres long-term, channeling the charged particles around themselves like Earth does with the solar wind, but on a far more intense scale. Yet despite these hostile conditions, the galaxy survives as a coherent structure. Stars continue to orbit in their patterns. Gas clouds persist in the outer regions beyond the immediate reach of the black hole's destruction. The galaxy isn't being torn apart or destroyed, it's coexisting with the monster at its heart, albeit uneasily, in a complex gravitational dance that has persisted for billions of years. This coexistence reveals something profound about the relationship between supermassive black holes and their host galaxies. They're not separate entities, predator and prey, but interconnected components of a single system that evolved together over cosmic time. The black hole regulates galaxy evolution through feedback mechanisms. The powerful jets and intense radiation from the quasar heat surrounding gas, preventing it from cooling and collapsing to form new stars. This limits and regulates the galaxy's continued star formation, preventing runaway growth. But the galaxy also feeds the black hole in an ongoing cycle. Gas from dying stars returns to the interstellar medium. Collisions between gas clouds compress material. Tidal interactions with neighbouring galaxies during close passes or mergers funnel gas toward the galactic centre. All this gas can eventually make its way inward, feeding the accretion disk and sustaining the quasar. The galaxy provides the fuel that keeps the central engine burning. Over billions of years, this relationship evolves through distinct phases. When the galaxy is young and gas-rich, as TON 618's host appears to be in the epoch we're observing, the black hole feeds vigorously. The quasar shines brightly, dominating the galaxy's energy output. Feedback mechanisms activate, heating gas and suppressing further star formation. Star formation rates drop dramatically. As gas supplies dwindle, consumed by star formation, heated and expelled by feedback or simply exhausted, the galaxy ages and quiets. The quasar fades as accretion slows to a trickle. The black hole goes, dormant but remains present, a massive gravitational anchor. The galaxy becomes quiescent, red and dead, dominated by old stars with little ongoing star formation. Millions or billions of years later, a major merger with another galaxy delivers fresh fuel. Gas clouds collide and lose angular momentum. Material streams toward the center. The black hole reawakens. The quasar reignites. The cycle repeats, driving another phase of activity before fading again. TON 618 appears caught in a vigorous active phase during the snapshot we observed 10 billion years ago. Or rather, it was in that phase. The light showing us this activity is ancient, showing us the galaxy as it existed when the universe was young. The galaxy is feeding its black hole enthusiastically. The black hole is shining, blazing across the cosmos. But this phase won't last forever. Eventually, whether it has already happened in the intervening 10 billion years or will happen in TON 618's future, the galaxy will exhaust its gas supply or feedback will blow it away. The accretion disk will thin and evaporate. The jets will sputter and shut down. TON 618 will go dark, not disappearing, still holding its 66 billion solar masses, but becoming invisible. A silent gravitational anchor at the center of a quiescent passive galaxy filled with aging red stars. And if some unfortunate traveler found themselves falling toward that anchor, descending past the point of no return, the black hole would subject them to the most brutal death imaginable. Not through crushing force, but through something far stranger and more horrifying. The ultimate spaghettification. Tidal forces represent the difference in gravitational pull between 2 points on an extended object. Stand on Earth, and gravity pulls your feet slightly harder than your head, because your feet are marginally closer to Earth's center. The difference is minuscule, completely unmeasurable by human senses, perhaps 1 part in 10 million. Your body experiences this differential as zero for all practical purposes. Near TON 618, that difference becomes catastrophically lethal. The defining mechanism of death, more dangerous in some ways than the black hole's event horizon itself. Imagine falling toward TON 618 feet first, descending from some distant starting point. Your feet are closer to the singularity than your head, just by the height of your body, perhaps 2 meters. At normal distances, this would be meaningless. But as you approach the immense gravitational field, the 2 meter difference starts to matter. Gravity pulls your feet harder than your head. The differential force grows. Near a stellar mass black hole, one formed from a collapsed star with an event horizon perhaps 20 kilometers across, this stretching would become extreme long before you reach the event horizon itself. The tidal gradient would be so severe that you'd be torn apart, ripped into pieces, reduced to a stream of atoms well outside the boundary. This process is called spaghettification, because objects get stretched like noodles before disintegrating completely. TON 618 is profoundly different. Its event horizon is so immense, 40 billion miles across, that the tidal gradient spreads out over truly cosmic distances. Gravity drops off more gradually across such vast scales. The curve is gentler. You could actually cross the event horizon intact, your body whole, experiencing uncomfortable but survivable tidal stress. The massive scale provides a grace period. For a time after crossing, you'd remain conscious and aware. The stretching would be noticeable, certainly, a pulling sensation, increasingly uncomfortable, your spine elongating slightly, joints separating marginally. But not immediately catastrophic, not instantly fatal. You'd have minutes, perhaps, to understand your situation, to grasp the inevitability of what's coming. As you fell deeper inward from the event horizon toward the singularity, a journey of 40 billion miles that would seem to take finite time from your perspective, the tidal forces would intensify progressively, at first gradually, then more rapidly, then exponentially. The pulling sensation would strengthen, your spine would lengthen further, joints would separate painfully. The stretching would transition from uncomfortable to painful to agonizing. Your bones would begin to creak under the stress, cartilage compressing and stretching beyond normal limits. Ligaments would strain, muscles would tear as the differential forces exceeded what biological tissue can withstand. The pain would be extraordinary. Every fibre of your being stretched simultaneously. But you wouldn't die from pain. There wouldn't be time for pain signals to fully register and process. The stretching accelerates faster than nerve impulses travel. As tidal forces continued growing, your body would lose structural integrity catastrophically. Ligaments would snap, muscles would rip, bones would fracture and then shatter completely under the differential stress. Eventually, perhaps seconds or minutes into your fall, depending on your trajectory and velocity, the tidal forces would overcome not just biological structural limits, but molecular bonds themselves. Your body would disintegrate into individual cells, each cell experiencing slightly different gravitational pull. Then cells would rupture, their membranes unable to maintain integrity against the tidal stress. Organelles would separate, molecules would tear apart. Continuing deeper, even chemical bonds would fail, complex organic molecules would break into simpler components, proteins would unfold and fragment, DNA helices would unwind and snap. Water molecules would separate into hydrogen and oxygen. Eventually you'd be reduced to individual atoms, carbon, hydrogen, oxygen, nitrogen, stretched into an ever-lengthening stream spiralling toward the singularity. Finally, if tidal forces grew strong enough near the singularity itself, though we don't know for certain what happens at that scale, even atomic nuclei might be disrupted. Protons and neutrons torn apart into their constituent quarks, matter itself deconstructed to its most fundamental components. You would cease to exist as anything resembling organized structure, reduced to a stream of elementary particles contributing infinitesimally to ton 618's mass. This process isn't unique to humans, it's universal, affecting anything falling toward TON 618. Stars experience spaghettification, planets get stretched and torn, asteroids, comets, gas clouds, all subject to the same tidal destruction. The difference is scale and how far something survives before disruption. A planet falling toward TON 618 might survive deeper into the gravitational well than a human would because planets are held together by much stronger forces, gravity binding their bulk, electromagnetic forces holding, rock together. A Jupiter-sized planet might survive even past the event horizon initially, stretched into an elongated ellipsoid but maintaining some coherence. But eventually, descending further, tidal forces would exceed even planetary binding energy. The planet would fragment, then shred into a stream of material spiraling inward. For TON 618, entire stars can cross the event horizon before being destroyed, a profound difference from smaller black holes. A star falling toward TON 618 might actually survive the crossing initially, continuing to shine and emit light even inside the event horizon for a time. But as it descended toward the singularity, tidal forces would eventually overcome the star's own self-gravity. The star would elongate, forming a stretched stream of plasma. The nuclear fusion in its core would disrupt as the star loses spherical shape. The stream would heat further through compression and friction, glowing intensely before finally plunging into oblivion. You can observe similar processes around smaller black holes through events called tidal disruption events. When a star wanders too close to a supermassive black hole, crossing inside what's called the tidal disruption radius, tidal forces exceed the star's self-gravity and rip it apart. Half the star's mass typically falls into the black hole. The other half gets flung outward at high velocity, escaping the system entirely. This disruption creates a brilliant flare of radiation lasting weeks or months. As the infalling material heats through compression and friction, it emits X-rays and optical light far brighter than the star's normal output. Telescopes regularly detect these tidal disruption flares from distant galaxies, sudden brightenings marking stellar deaths. Each event adds perhaps half a solar mass to the central black hole, not much individually, but cumulatively significant. TON 618 likely experiences tidal disruption events regularly given its enormous gravitational reach. Its sphere of influence, the region where its gravity dominates, extends light years from the centre. Stars throughout this region orbit the black hole directly. Some fraction inevitably wander onto doomed trajectories, crossing inside the disruption radius. Each disruption adds mass incrementally while producing a brief flare of radiation. From 10 billion light-years away, we cannot resolve individual tidal disruption events at TON 618. They're too brief and too faint compared to the quasar's overwhelming steady output. But statistically, they must occur, contributing to the overall luminosity we measure and the black hole's gradual growth. The spaghettification process reveals gravity's true violence. We think of gravity as a gentle force, the thing keeping us grounded, making apples fall, holding planets in orbit. It seems predictable, safe, manageable. Near black holes, gravity transforms into a weapon that tears reality itself apart at the seams, reducing organized matter to its most fundamental components through sheer differential force. But even spaghettification, as horrific as it sounds, isn't the strangest effect operating near TON 618. There exists a region closer than the event horizon where light itself behaves impossibly, where photons can orbit in circles, where you could theoretically see the back of your own head by looking forward, the photon sphere and beyond. The event horizon marks where escape velocity equals light speed, the ultimate boundary, but there exists another critical radius closer to the black hole where gravity affects light in extraordinarily bizarre ways. This is the photon sphere, and for TON 618, it sits at 60 billion miles from centre, exactly 1.5 times the event horizon radius. At this precise distance, gravity is strong enough to bend light into circular or spiral orbits around the black hole. Photons travelling tangent to the photon sphere at exactly the right angle will orbit indefinitely in a perfect circle around TON 618, neither falling inward nor escaping outward, at least in theory, assuming perfect conditions. This creates impossible optical effects that challenge human intuition about light and vision. If you somehow hovered just outside the photon sphere, suspended there by some impossibly powerful engine, and looked sideways perpendicular to the black hole, you would see light that had orbited completely around TON 618 potentially multiple times. Light could circle the black hole 360 degrees and return to its starting point. This means you could theoretically see the back of your own head by looking forward. Photons leaving the back of your skull would travel sideways, curve around the black hole following the warped space-time geometry, complete a full orbit, and enter your eyes from the front. You'd see yourself from behind, your own back, your own neck, the back of your own head, creating impossible visual recursions that violate normal causality. Multiple images of the same object could appear, each representing light that orbited a different number of times before reaching you. The photon sphere becomes a kind of cosmic mirror, bending and reflecting light in ways that create surreal, M.C. Escher-like visual paradoxes. The photon sphere is fundamentally unstable, however. Any slight deviation from perfect tangential motion, any tiny perturbation, inward or outward, causes the photon to choose a fate. Nudge slightly inward and the photon spirals toward the event horizon, eventually crossing and disappearing. Nudge slightly outward and the photon escapes to infinity, travelling away from the black hole forever. Real photons don't remain in the photon sphere for extended periods. They might orbit once, perhaps twice if conditions are extraordinarily precise, then either fall in or escape. But the boundary represents a critical point in space-time geometry, the innermost region where light can exist in orbit, however temporarily, before being forced to decide between falling and escaping. Light attempting to orbit in the photon sphere experiences extreme gravitational redshift. Photons must constantly fight against gravity to maintain their circular path, losing energy in the process. From the perspective of a distant observer, light in the photon sphere appears dimmer and redshifted, shifted toward lower energies and longer wavelengths, as photons sacrifice energy climbing partway out of the gravity well even while remaining in orbit. For TON 618, the photon sphere at 60 billion miles represents a volume larger than most stellar systems, a region where the geometry of space-time has become so warped that straight lines curve back on themselves, where the normal rules of optics fail completely. Closer still than the photon sphere, in the region between it and the event horizon, exists another exotic structure found only around rotating black holes, the ergosphere. This region is where frame dragging, the rotation of space-time itself, becomes so extreme that remaining stationary becomes physically impossible. TON 618 almost certainly rotates. Most black holes do, inheriting angular momentum from the material that formed them and from the matter they've consumed. Rotating black holes drag space-time around them like a whirlpool dragging water, a phenomenon called frame dragging or the lens-thirring effect. Inside the ergosphere, the region between the outer boundary called the ergosurface and the event horizon, space-time rotates so severely that you cannot remain stationary relative to distant stars. Even if you fired your engines at maximum thrust trying to hover in place, you would be forced to orbit in the same direction as the black hole's rotation. Space-time itself is moving, carrying you with it unavoidably. You could still escape from the ergosphere, it lies outside the event horizon, but you could not stand still. The geometry of space demands motion. This isn't a technological limitation, it's fundamental physics. The structure of space-time inside the ergosphere forbids stationary positions. The ergosphere represents a region where the black hole's rotation has warped space-time so thoroughly that even the concept of at rest loses meaning. Everything must move, must rotate with the black hole, must participate in the cosmic whirlpool. For TON 618, both the photon sphere and ergosphere extend across distances comparable to planetary orbits in our solar system. Neptune orbits roughly 2.8 billion miles from the Sun, but the photon sphere sits at 60 billion miles, more than 20 times farther. These aren't compact regions measured in kilometers. They span cosmic distances, volumes of space where exotic physics dominates and normal intuition fails. Imagine a hypothetical advanced civilization capable of approaching these regions with sophisticated spacecraft and instruments. They could potentially harvest energy from the black hole's rotation using a process called the Penrose mechanism. By carefully dropping matter into the ergosphere at precisely calculated angles, they could extract rotational energy from TON 618 itself. The physics works like this. Matter enters the ergosphere and splits into two pieces. One piece falls into the black hole, crossing the event horizon and vanishing. The other piece escapes, but through careful orchestration of the trajectory, the escaping piece carries more energy than the original object had. The extra energy comes from the black hole's rotation, stolen from its angular momentum store. The black hole spins slightly slower. The escaped matter carries away the difference as kinetic energy. This isn't science fiction or speculation. The physics is rigorously proven, derived from general relativity. Roger Penrose described this mechanism mathematically in 1969. A sufficiently advanced civilization could theoretically use a rotating black hole as a power source, gradually spinning it down while extracting enormous amounts of energy, potentially millions of times more energy than nuclear fusion provides. The energy available from a massive rotating black hole like TON 618 is staggering. The rotational energy stored in its twisted spacetime equals a substantial fraction of its rest mass, potentially billions or trillions of solar masses worth of energy, convertible to useful work through the Penrose process. Tapping even a tiny percentage would provide power beyond anything achievable with stars or conventional energy sources. But approaching close enough to utilize this mechanism would be extraordinarily dangerous, perhaps impossible even for advanced civilizations. The tidal forces, while gentler than near smaller black holes, remain deadly at close range. The intense radiation environment from the accretion disk, if the black hole is actively feeding, would sterilize any spacecraft or crew. Frame dragging effects would complicate navigation profoundly, and the ever-present risk exists that one navigational error, one thruster failure, one miscalculation sends you past the point of no return. What would that final journey look like? What would you see? What would you experience as you fell into TON 618, past the photon sphere, through the event horizon, toward the singularity? Let's descend together and find out. The fall into darkness. The first thing you would notice approaching TON 618 is the distortion, not of your body, but of light and space around you. As your spacecraft descended from safe distance toward the black hole, light from the universe behind you would bend around TON 618 following curved spacetime. Stars would appear to shift position, sliding across the sky as their light paths warped. The black hole would loom ahead, but you wouldn't see it directly. You'd see an absence, a perfect circle of absolute darkness against the background stars. Around that darkness, the accretion disk would blaze if TON 618 were actively feeding. Not a simple ring, but a warped, twisted structure defying normal geometry. Light from the far side of the disk, the side facing away from you, would curve around the black hole's sphere and reach your eyes. You'd see both the front and back of the disk simultaneously, creating an impossible view. The disk would appear to wrap around the black hole, sphere vertically, creating a complete halo of light above, below, and around the central darkness. Colours across the disk would shift dramatically due to gravitational effects. Light climbing toward you from deeper in the gravity well would be gravitationally redshifted, stretched to longer wavelengths, shifted toward the red end of the spectrum and beyond into infrared. Light from regions at higher gravitational potential would be blue shifted, compressed to shorter wavelengths, shifted toward blue and ultraviolet. The disk would display a complex gradient, reds near the centre where gravity is strongest, blues toward the edges where space-time is flatter. But the pattern would be complicated by Doppler shifts from the disk's rotation and by relativistic beaming effects. As you fell closer, the black circle would grow, consuming more of your field of view. It would expand to dominate the sky, a sphere of perfect darkness outlined by the brilliant warped disk. The disk would appear to rise up around you, curving overhead and below, wrapping around your position as perspective shifted. Normal geometry would fail completely. The visual field would become increasingly distorted, curved, impossible. Light from stars behind you would converge, pulled inward by the black hole's gravity. You'd see the entire universe behind you compressed into a shrinking circle as light paths bent more and more severely. Stars would crowd together, overlapping, their position shifted by gravitational lensing. As you approach the event horizon, that circle would collapse smaller and smaller, condensing the cosmos behind you into an ever tinier point. Ahead, the event horizon wouldn't look like a surface or barrier. It would appear as a deepening void, a bottomless pit in space, pure blackness, absolute and perfect. No light escapes from beyond the horizon, so there's nothing to see, just darkness. The boundary itself would be invisible, unmarked, impossible to detect visually until you crossed it. Crossing the event horizon would feel like nothing. No barrier, no jolt, no sensation at all. Just a mathematical boundary in space-time that you pass through like walking through a doorway. You'd remain intact, conscious, aware. Your instruments might register the crossing, gravitational field strength reaching a critical value, time dilation diverging toward infinity, but you personally would feel unchanged. But everything would have fundamentally changed. The singularity would no longer be a point in space ahead of you, a destination you're travelling toward. It would transform into a moment in your future, an instant in time that you're hurtling toward inevitably. No matter which direction you accelerated your engines, no matter how you manoeuvred or thrust, you would move closer to the singularity in time rather than space. You couldn't avoid it by turning around any more than you can avoid tomorrow by facing backward. Inside the event horizon, time and space have exchanged roles in a sense. Outside, you can move freely in space, forward, backward, left, right, but are forced to move forward in time. Inside, you're forced to move forward in the radial direction toward the singularity, what used to be a spatial direction, while time becomes almost navigable in weird ways we don't fully understand. The mathematics predicts closed time-like curves, paths through space-time that loop, back on themselves, but most physicists believe these are artifacts of the theory breaking down rather than real physical possibilities. Looking back toward the universe outside, you would see time accelerate dramatically. Stars would move faster across the sky. Planets would whip around their orbits. Galaxies would spin, collide, merge and separate, their evolution playing out rapidly. The entire future history of the cosmos would unfold before your eyes, in subjective minutes. This is gravitational time dilation in reverse. From your perspective, deep in the well, the universe outside appears to speed up, racing through time while you experience normal flow. The accretion disk would still be partially visible but increasingly distorted. Light would bend in impossible ways, following curved paths through the extreme space-time geometry inside the horizon. You might see multiple images of the same disk features, ghost images representing light that has orbited around weird trajectories before reaching you. The visual field would be chaotic, full of artifacts and strange effects as light paths tangled through warped space. As you fell deeper inward from the horizon toward the singularity, covering that 40 billion mile gap, tidal forces would begin their work with increasing intensity. The stretching would start gently but escalate. Your body would elongate progressively. Pain would surge through you as bones separated, ligaments tore, muscles ripped. But the forces would escalate faster than your nervous system could process. Disintegration would follow, your body tearing apart into cells, then molecules, then atoms. The final moments would be incomprehensible. Time and space would lose distinction. The geometry would become infinitely curved. Physical laws as we understand them would break down completely. The singularity would approach, a point of infinite density, infinite curvature, where all mass concentrates, and then your existence would end. You would be gone, consumed, integrated into Ton 618's mass, contributing infinitesimally to its total. Your information, your structure, your history, all potentially lost forever, raising deep questions about information conservation we'll explore later. And what would an outside observer see during all this? To someone watching from safe distance, your fall would appear to last forever, literally infinite time. You would never reach the event horizon from their perspective. You would slow down progressively, asymptotically approaching the boundary. You'd freeze there, suspended in eternal falling, your image gradually fading as photons redshifted beyond detection. From the outside, you'd become a ghost frozen at the edge, fading to invisibility over seconds or minutes, never quite crossing despite having crossed from your own perspective long ago. This isn't illusion. Both perspectives are real. Relativity asserts there's no single absolute time. What happens to you and what appears to happen from distance can differ fundamentally, yet both are true in their respective reference frames. This paradox captures the profound weirdness of black holes. They're not just objects in space, but portals to regions where our intuitive understanding of time, space, and causality breaks down entirely. And at the very center, where you'd ultimately arrive, lies the singularity, the point where physics admits complete defeat. The singularity, where physics dies. At the center of Ton 618, all 66 billion solar masses compress into a single point. Not a small object, not a dense sphere, a mathematical point with zero volume and infinite density. This is the singularity, the place where space-time curvature becomes infinite, where physics as we understand it completely breaks down, where our best theories produce nonsensical infinities instead of meaningful predictions. General relativity predicts singularities inside black holes. The equations demand it. As matter collapses under its own gravity with nothing to stop it, no pressure, no force sufficient to oppose gravity's pull, density increases without limit. Matter crushes down to a geometric point where curvature of space-time becomes infinite. The mathematics is clear but almost certainly incomplete. Infinity in physics typically signals that your theory has reached its limits, that you're extrapolating beyond where the model applies. When equations give infinite answers, they're essentially admitting failure. At the singularity, general relativity stops providing meaningful predictions. The theory breaks down, becomes inapplicable, fails. We don't know what actually happens at the singularity. Does matter truly compress to zero volume? Does density actually reach infinity? Or does something else occur? Something that requires a theory of quantum gravity we don't yet possess to properly describe. String theory, loop quantum gravity, and other attempts to merge quantum mechanics with general relativity suggest the singularity might not be infinitely small or dense. Quantum effects might prevent complete collapse. There might be a minimum size, perhaps the Planck length, approximately 1.6 times 10 to the power of minus 35 meters, beyond which space itself becomes granular and continuous collapse becomes impossible. The Planck length is unimaginably small, far, far smaller than an atomic nucleus, smaller than an electron, smaller than any scale we can currently probe experimentally. But it's not zero, it's finite. If quantum gravity prevents collapse below this scale, the singularity would be a Planck-sized object rather than a true point, still incomprehensibly dense, but not infinite. Another possibility is that singularities have structure rather than being simple points. For rotating black holes, called Kerr black holes, general relativity predicts the singularity forms a ring rather than a point. The rotation creates angular momentum that prevents collapse to a single point, instead creating a circular singularity located in the equatorial plane of the black hole. The mathematics of Kerr black holes predicts even stranger features: closed time-like curves inside the event horizon, pathways through space-time that loop back on themselves temporally, theoretically allowing time travel. The equations also predict wormholes connecting to other regions of space-time, or even other universes. Few physicists believe these features are physically real. They're more likely artifacts of the theory extending beyond its valid domain. We have absolutely no way to observe singularities directly. They're hidden behind event horizons. Light cannot escape to carry information outward. We cannot send probes that could report back. Everything that crosses the event horizon is lost to outside observers forever. The singularity remains fundamentally inaccessible to direct study. This leads to one of physics' great unsolved problems, the information paradox. In quantum mechanics, information is fundamentally conserved. You cannot destroy it. The quantum state of a system can evolve and change, but information about that state persists, encoded in the quantum configuration. Destroying information would violate unitarity, a core principle of quantum mechanics. But if matter falls into a black hole and reaches the singularity, where does the information about that matter go? Does it disappear? That violates quantum mechanics. Does it remain encoded somehow in the black hole? How? The matter has crossed the event horizon, fallen to the singularity, and, if singularities are real, been crushed out of existence. Stephen Hawking originally proposed that black holes evaporate over time through quantum radiation, eventually disappearing completely. But Hawking radiation is thermal, random, carrying no information about what fell in. If a black hole evaporates entirely, leaving only random radiation, the information about everything that fell in would be lost. This violates quantum mechanics profoundly. Hawking wrestled with this paradox for decades. Eventually he conceded that information must somehow be preserved, perhaps encoded in the Hawking radiation in subtle quantum correlations, too complex to observe directly. But exactly how information escapes, what mechanism preserves it, remains unknown and hotly debated. For TON 618, Hawking radiation is completely negligible and irrelevant on any practical timescale. We'll discuss this more later, but the information paradox remains conceptually crucial. If TON 618 has consumed 66 billion solar masses worth of stars, gas, and who knows what else over its lifetime, where is the information about all that matter? Lost forever? Preserved somehow? We don't know. The singularity at TON 618's heart represents the ultimate edge of human knowledge, a boundary beyond which our physics fails, our mathematics produces nonsense, our intuition provides no guidance. We know it must exist in some form because the equations demand it. We know it hides behind the event horizon, inaccessible to observation. We know it marks the endpoint of anything that falls in. But what it actually is, what occurs there, what happens to matter and information, these remain profound mysteries that will likely persist until we develop a complete theory of quantum gravity capable of describing Planck-scale physics in extreme gravitational fields. Solving the singularity problem, understanding what happens at black hole centers, would revolutionize physics. It would require unifying quantum mechanics and general relativity, the two great theories of 20th century physics that remain fundamentally incompatible. Making progress on this problem is one of theoretical physics' primary goals. TON 618, with its extreme scale and mass, represents a unique laboratory for contemplating these questions, though only theoretically, since we'll never observe its singularity directly. The extreme conditions there push our theories to their absolute limits and beyond, exposing gaps in our understanding and pointing toward the physics we still need to discover. And if black holes confuse us, the fact that TON 618 will essentially never evaporate makes the mystery even more profound and permanent. Other giants in the cosmos, TON 618 is extraordinary, but it's not definitively alone at the extreme upper end of the black hole mass spectrum. Other supermassive black holes rival or possibly exceed its mass, representing the absolute limits of what can form in our universe. Phoenix A holds the current record by some estimates. Located at the centre of the galaxy cluster Abell 2744, roughly 5.7 billion light-years away, Phoenix A weighs approximately 100 billion solar masses, potentially 50% more massive than TON 618. Though measurements carry substantial uncertainty, Phoenix A is surrounded by one of the most powerful radio sources ever detected. The jets extend for millions of light-years, carving enormous cavities in the hot intra-cluster gas. The energy required to excavate these cavities is almost incomprehensible, equivalent to the total energy output of billions of galaxies over millions of years. The cavities visible in X-ray observations testify to Phoenix A's incredible past activity. But Phoenix A's mass estimate comes with large error bars. Different measurement techniques yield results ranging from 50 billion to over 100 billion solar masses. The distance and observational difficulties make precise measurements extremely challenging. Some analyses suggest Phoenix A might be lighter than TON 618, while others confirm it as more massive. The uncertainty means the most massive black hole title remains contested. Holmberg 15d. A is another extreme contender. This black hole sits at the centre of the supergiant elliptical galaxy, Holmberg 15a, roughly 700 million light-years away. Much closer than TON 618, but still distant. Mass estimates range wildly from 40 billion to 170 billion solar masses, depending on the methodology used. Holmberg 15a formed through multiple galaxy mergers. The black hole consumes several smaller supermassive black holes over billions of years, growing to its current enormous size. The surrounding galaxy shows signs of this. Violent history. The core is unusually large and depleted of stars, likely due to gravitational interactions during mergers flinging stars outward. S50014 plus 81 is a quasar even more distant than TON 618, sitting about 12 billion light-years away. The black hole weighs approximately 40 billion solar masses. Like TON 618, it existed when the universe was young, presenting the same formation timeline problems. How did it grow so large so quickly? The question remains unanswered. SDS-SJ1030 plus 0524 is another early universe quasar at 12.8 billion light-years distant. The black hole weighs roughly 12 billion solar masses and appeared when the universe was less than 1 billion years old, one of the earliest known supermassive black holes. Its existence challenges our understanding of black hole formation in the universe's first billion years. These early massive black holes all violate expectations. They appeared too soon, grew too fast, became too massive for standard models to explain. Everyone requires exotic formation scenarios or super Eddington feeding rates sustained for hundreds of millions of years. NGC 1277 contains a remarkable black hole weighing 17 billion solar masses in a galaxy much smaller than the Milky Way. The black hole represents about 14% of the galaxy's total stellar mass, an absurdly high fraction. For comparison, Sagittarius A star is less than 0.1% of the Milky Way's stellar mass. NGC 1277's black hole is disproportionately massive for its galaxy, suggesting unusual formation history or evolution. Theoretical limits suggest black holes cannot grow arbitrarily large. Feedback mechanisms shut down growth. Fuel supplies exhaust. The universe's expansion separates galaxies, reducing merger rates and fuel delivery. Somewhere there's a maximum practical mass for black holes in our universe. Current estimates place this limit around 100 billion solar masses, possibly higher under perfect conditions. Phoenix A may be approaching this limit. If so, it represents the largest black holes that can form given the universe's age, expansion rate, and physical laws. But measurements of these extreme objects remain uncertain. Many sit at immense distances where observational challenges complicate mass determinations. Error bars span tens of billions of solar masses. The true ranking of most massive black holes may shift as better data arrives from improved telescopes and measurement techniques. What is clear is that the universe has produced multiple monsters. TON 618 is extraordinary, but not unique. Supermassive black holes weighing tens or hundreds of billions of solar masses exist in various locations across cosmic history. Each one is a marvel, pushing the boundaries of what's possible under known physics. These black holes also serve as crucial scientific laboratories. Their extreme gravity tests general relativity in the strongest field regime accessible to observation. Their formation history constrains models of galaxy evolution and early universe structure formation. Their influence on surrounding matter reveals how the universe transitions from smooth, post-Big Bang conditions to the structured cosmos we observe today. Discovering and characterizing these extreme objects represents one of astronomy's ongoing frontiers. Each new detection teaches us something about the universe's capacity for creating massive structures and the physical processes operating in the early cosmos. And even neutron stars, the densest objects besides black holes, would not survive an encounter with TON 618, when neutron stars meet their end. Neutron stars are the densest objects in the universe aside from black holes themselves. A neutron star packs 1 to 2 solar masses into a sphere only 20 kilometers across. 1 teaspoon of neutron star material would weigh 1 billion tons on Earth. The matter is compressed so severely that protons and electrons merge into neutrons. The entire star is effectively a single giant atomic nucleus held together by neutron degeneracy pressure. This degeneracy pressure is what prevents neutron stars from collapsing further into black holes. It's quantum mechanical in origin. The same principle that prevents electrons from occupying the same quantum states prevents neutrons from being compressed beyond a certain density. Neutron stars survive supernova explosions that destroy normal stars. Their surfaces are solid, harder than diamond, made of exotic nuclear matter. They seem indestructible. But against TON 618, even a neutron star is fragile. If a neutron star wandered close enough to the black hole, tidal forces would overwhelm even neutron degeneracy pressure and tear it apart. The process would be violent and rapid. As the neutron star approached, tidal forces would begin stretching it. The near side experiences stronger gravity than the far side. For most objects, stretching begins gently. But neutron stars resist deformation stubbornly. Their internal pressure is enormous, comparable to nuclear forces. The star maintains its spherical shape tenaciously. Close to TON 618, tidal forces would eventually exceed the star's structural strength. The neutron star would begin elongating despite the resistance. The deformation would accelerate through positive feedback. As the star stretches, tidal forces on the elongated regions increase further, accelerating the stretching. Within seconds, the neutron star would transition from sphere to elongated ellipsoid to cigar shape. Then disintegration. Tidal forces would overcome neutron degeneracy, pressure entirely. The star would fragment into streams of neutron-rich matter spiraling toward TON 618. The disrupted material would heat tremendously through compression as it spiraled inward through the accretion disk. A neutron star carries gravitational binding energy equivalent to about 10 to 15% of its rest mass. When torn apart, this energy converts partially to kinetic energy and radiation. The result would be an extraordinarily bright flare, far brighter than normal stellar tidal disruptions. The flare would be visible across the galaxy and potentially detectable from Earth, despite the 10 billion light-year distance if we happen to observe during the event. X-rays and gamma rays would dominate the spectrum as neutron-degenerate matter heated to billions of degrees. The disrupted material would behave differently from normal stellar matter. Neutrons are unstable outside nuclear environments. Free neutrons decay into protons, electrons, and neutrinos within about 15 minutes. The stream of neutron-rich matter spiraling into TON 618 would rapidly convert into ordinary matter through neutron decay, releasing additional energy. Some material might not fall immediately into the black hole. Part of the disrupted neutron star could be flung outward at high velocity, escaping the system entirely. This ejected material would seed surrounding space with heavy elements, including rare isotopes produced in the extreme conditions of the disruption, potentially including our process elements like gold, platinum, and uranium, formed through rapid neutron capture. The frequency of neutron star disruptions near TON 618 is unknown, and likely extremely low. Neutron stars are rare. They form only from massive star supernovae. Most orbit safely in binary systems or drift through relatively empty space. The probability of one wandering close enough to a supermassive black hole for tidal disruption is tiny. But in the crowded environment near TON 618, where stellar density is high and gravitational interactions frequent, such encounters are possible even if rare. Over billions of years, perhaps dozens or hundreds of neutron stars have been disrupted, each contributing 1 to 2 solar masses to the black hole and producing brilliant flares. Each disruption would also produce gravitational waves. The final moments before breakup involve a compact object spiraling rapidly in a strong gravitational field. The space-time distortion generates waves detectable potentially by future instruments like LISA, if the event occurred recently enough for the waves not to have passed Earth yet. Observing such an event would provide invaluable scientific data. It would probe matter at nuclear densities, test general relativity in extreme gravitational fields, and reveal how tidal forces operate near massive black holes. The spectroscopic data from the flare would show the composition and structure of neutron star material, testing nuclear physics theories. TON 618, with its immense gravity and large sphere of influence, would be an ideal laboratory for such studies, though purely theoretical since we cannot observe it in sufficient detail across 10 billion light-years. Neutron star disruptions represent just one of many exotic phenomena that might occur in TON 618's vicinity. The extreme environment creates opportunities for rare events and processes we can barely imagine. Each event teaches us about physics in regimes inaccessible by any other means, and ultimately, TON 618 represents the ultimate mystery, a challenge to our understanding that may never be fully resolved. The ultimate mystery, TON 618, embodies some of cosmology's deepest unsolved mysteries. Its existence challenges our theories. Its formation remains unexplained by standard models. Its interior is forever hidden behind an event horizon we can never penetrate. It represents the ultimate edge of human knowledge. The formation problem persists. How did 66 billion solar masses accumulate in less than 3 billion years? Standard accretion at the Eddington limit cannot explain it. Super Eddington feeding helps but requires sustained extreme conditions. Primordial black holes offer a head start but lack observational evidence. Mergers could build mass quickly but require improbably frequent encounters. The answer likely involves a combination of factors we don't fully understand. The early universe was different from today in ways our models may not capture completely. Perhaps gas was denser and more efficiently funneled toward black holes. Perhaps magnetic fields played a stronger role in accretion than current theories predict. Perhaps dark matter interactions enhance growth through mechanisms we haven't discovered. Solving the formation mystery would revolutionize cosmology. It would teach us about the first billion years of cosmic history, about galaxy formation, about how structure emerged from the smooth post-Big Bang universe. The answer likely requires new physics, or at least significant revisions to existing models. The information paradox remains unresolved. What happened to all the information about the 66 billion solar masses that fell into TON 618? Is it preserved somehow, encoded in Hawking radiation, or on the event horizon? Or has it been destroyed, violating quantum mechanics? Resolving this paradox requires unifying quantum mechanics and general relativity, a problem that has resisted solution for decades. The singularity remains forever inaccessible. We can never observe it directly. We can never test theories of what actually happens at infinite density. The mathematics breaks down, producing meaningless infinities. Understanding the singularity requires quantum gravity, a complete theory we don't yet possess. TON 618 will outlast virtually everything in the universe. It will remain long after stars have burned out, after galaxies have dispersed, after protons have potentially decayed. It represents one of the most permanent structures imaginable, lasting 10 to the power of 100 years until Hawking radiation finally erodes it to nothing. Yet despite its permanence, we know so little. We see only ancient light from 10 billion years ago. We cannot observe its current state. We cannot study its immediate environment in detail. We can only infer, calculate, theorize based on observations of distant photons. TON 618 reminds us how much remains unknown. The universe is vast, ancient, complex, beyond human comprehension. We've made tremendous progress understanding it through physics, astronomy, mathematics. But objects like TON 618 expose the limits of our knowledge. What lies inside the event horizon? What is the true nature of the singularity? How did this monster form so quickly? Does information survive or perish? Can quantum mechanics and gravity be reconciled? These questions remain open, actively researched, far from resolution. Future telescopes and instruments may provide new insights. The James Webb Space Telescope observes the early universe in unprecedented detail, potentially finding even earlier, more massive black holes. LISA will detect gravitational waves from supermassive black hole mergers. Next-generation radio telescopes might resolve TON 618's structure more clearly, but some mysteries may persist. The event horizon is an absolute information barrier. Whatever lies beyond may be forever unknowable. The singularity might represent a fundamental limit to scientific knowledge, a place where physical law ceases and our theories fail completely. TON 618 stands as a monument to both human achievement and human limitation. We discovered this object across 10 billion light-years of space. We measured its mass, distance, luminosity. We calculated its properties, predicted its behavior, understood its place in cosmic evolution. This represents extraordinary scientific progress, yet we cannot answer the most basic questions. How did it form? What happens inside? Where did the information go? These mysteries persist, humbling us with their depth, and that, perhaps, is TON 618's greatest lesson. The universe is vast beyond imagination, filled with wonders and horrors that challenge our comprehension. Objects exist that shouldn't be possible according to our carefully constructed theories. Mysteries persist that may never be solved. The edge of knowledge is closer than we'd like to believe. TON 618 is the monster in the cosmic darkness, a gravitational leviathan that bends space-time, devours stars, and defies explanation. It existed when the universe was young. It may still exist today, dark and silent, waiting. It will exist long after humanity is extinct, after Earth is gone, after our sun has died. It is the ultimate reminder that we are small, temporary, and surrounded by forces we barely understand, and that makes it, paradoxically, one of the most important objects in the universe for us to study, question, and contemplate.